Hello, everyone. Today we're going to start talking about the information in Chapter 19, which is on bonding. The beginning of Chapter 19 focuses on your molecular or covalently bonded compounds. And so in the introduction, you get information about bonds and what bonds actually are. In the first section of the chapter, that's where we start talking about our Lewis structures. And again, please remember, Lewis structures are used to show how covalently bonded elements are bonded together. Your book then proceeds to talk about what valence electrons are. Valence is a major term that you'll need to know for chemistry. And so what I need you to remember is that we're talking about electrons that are in the outermost energy level of whatever your element is. And so for most elements, the maximum number of valence electrons they can have is 8. If your element is in an A group, then the number in front of the A tells you how many valence electrons there are. So if it's in column 1A or column 1, then there's 1 valence electron. If it's in column 14 or 4A, that means there are 4 valence electrons. And so then when we jump to column 18, there are 8 valence electrons. Now, please remember, this only works on your A groups. It does not work on your B groups at all. So you can't determine the number of valence electrons by the column number for a B group. But you won't really have to deal with that many of those B group elements in this first section, which is on Lewis structures. And so when you draw a Lewis structure, if you're drawing a Lewis structure for an element, all you do is place the symbol of the element in the center, and then you surround it with the number of dots that corresponds with how many valence electrons there are in that structure. So if we had the element boron, we would write the symbol for boron, which is going to be a capital B. And then because boron's in column 13 or column 3A, we would show 3 dots surrounding that boron. Now, when you draw your dots, the biggest rules are that you have to have 1 dot on each side before you put 2 dots on any side. And so for boron, it would not matter what 3 sides we put the 1 dot on, but again, you have to have 1 dot on each side before you put 2 dots on any. Or if we were to draw the Lewis structure for the element oxygen, we would write the symbol for oxygen, and then oxygen's in column 16 or column 6A, which means I need 6 valence electrons. So again, I have to have 1 dot on each side before I put 2 dots on any side. And then it does not matter what 2 sides I show those double electrons on. Okay, and so that's how you would draw your Lewis structure for elements. Now, when we move on in the chapter, the next thing it talks about is the octet rule. And what that rule says that is that an atom has a maximum stability when it's surrounded by 8 valence electrons, with the exception of hydrogen, which can only have 2. So remember, those elements on row 1, they can only have 2 electrons. So we're talking about hydrogen and helium. For the most part, helium you'll never have to show in a compound because it doesn't really bond because it's stable with 2 valence electrons. And please remember that on row 1, the most number of electrons you can have is 2. When you move down to the other rows on the periodic table, though, most of those elements want to get 8 as their valence electron number. All right, and so in your Lewis structures, we generally show a line to show that elements are bonded to one another. And so if we were to draw the Lewis structure for, let's say, H2O, we would have an O bonded to 2 H's, and then we would need our dots so that we completed our octet. Okay, and so for hydrogen, or for the molecule water, you see this would be our correct Lewis structure for that molecule. Now, your book then goes into talking about how you draw Lewis structures and the rules for doing those Lewis structures. The very first thing you want to remember, though, is that before you draw a Lewis structure, you need to count how many valence electrons you have for the elements that are present in your compound. Once you count those, you need to determine which of the elements goes in the center. And the rule generally is the element that's further to the left on the periodic table or further down the periodic table is going to be the element that is in the center, because that is the most electropositive element. All right, once you do that, you've got to give elements in your diagram from the pool that you calculated of valence electrons, the correct number of electrons they need to be stable. Remember, with hydrogen, because it can have no more than 2, once you've drawn one line to hydrogen, hydrogen is done. But any other elements, you need to try to give them 8 valence electrons. And so on this oxygen, if we count, we know each line represents 2 electrons. So I've got 2, 4 electrons, and then I need 4 dots, which represent your lone pairs of electrons. I remember a pair is 2 electrons, which is why we have 2 pairs of electrons around that oxygen atom. Your book then gives you a really good summary of how your Lewis structure should look on page 378. It gives you a chart with the number of bonds and lone pairs that you would expect for each of your central atoms across the second row. If you have any questions on any of those, please reach out and ask those, because in section 19.2, that's where we move to our molecular shapes and bond angles. And now the biggest thing that you need to understand is that in order to get the correct molecular shape and bond angle, you have to first draw the Lewis structure. So you have to have your Lewis structure drawn before you can look at the molecular shape or the bond angle. Now, the model that we use to predict molecular shape is our VSEPR model, valence shell electron pair repulsion. And according to that model, electrons that are non-bonding are going to take up more space than electrons that are bonding electrons. And so we want to minimize the amount of repulsion there is in our atom between, or in our compound between the electrons. And so the VSEPR theory best orients those atoms in the molecule the correct way so that the non-bonding electrons get as much space as they possibly can get, and your bonding electrons, they actually use less space, again, because those electrons are being shared. So in order to predict the shape of your covalent molecule, you have to look at your central atom for VSEPR. And with VSEPR, you're looking at around that atom in the center, how many bonding pairs of electrons are there and how many lone pairs of electrons are there. If all of your atoms are bonded to the central atom and there are no lone pairs, then that is the molecular geometry that shape is going to take. If you've got 2 atoms that are bonded to one another, then you know that structure is going to be linear. If you've got 3 atoms being bonded to your central atom, then they will have bond angles of about 120 degrees, and that orientation is called trigonal planar. That orientation is called trigonal planar. When you've got 4 bond pairs around your central atom and no lone pairs, then it's going to take a tetrahedral orientation. And in that tetrahedral orientation, you're going to have bond angles of about 109.5 degrees. Because again, that gives all of the non-bonding electrons as much space as they need to spread out away from one another. Now, when you've got elements that have more than 4 pairs of electrons around them, your molecular geometries can take on some interesting shapes, but in all the situations that we've talked about so far, we've talked about what happens when you only have bonding electrons. Well, what happens if you've got non-bonding electron? So in the example of NH3, when I look at the Lewis structure for it, when I calculate those values, I'm going to do the valence electrons for nitrogen, which I know are 5. I'm going to look at the valence electrons for 3 hydrogens, which I know that each hydrogen has a valence number of 1, but because there are 3 of them, that gives us a grand total of 8. I add those numbers together, I get my 8. My nitrogen I know goes in the middle because hydrogen never can. So I have the nitrogen in the middle, and to that nitrogen, I'm going to attach these 3 hydrogens. Now, from our pool of 8 electrons, I drew 1, 2, 3 lines, which means that I used already 6 electrons. Because remember, 1 line equals 2 electrons. Now, that leaves me with 2 electrons in my pool. So when I start to count to make sure everything has what it needs to be stable, I notice that each one of my hydrogens do have what they need to be stable. But on my nitrogen, I've only got 6 electrons, but I want 8 electrons. And so, because I've got 2 extra electrons and nitrogen does not have its 8, I would place those 2 electrons on the nitrogen atom, which gives us, notice I've got 4 pairs of electrons around the central atom, but 3 of them are bond pairs and only 1 of them is a lone pair. Now, because of this, we would expect that the orientation should be tetrahedral. And again, that's because of the 4 pairs of electrons around the central atom. But what we actually find is that this molecule actually forms a trigonal pyramidal orientation. Now, it's trigonal pyramidal because those 3 hydrogens are in the same plane, but the nitrogen is not in the same plane as those 3 hydrogens. In your trigonal planar, they're all in the same plane. Your central atom and your actually substituent atoms, which are those that are connected to that central atom. They're all in the same plane in trigonal planar. But when you add that lone pair of electrons, because lone pairs need more space than bond pairs, then you actually reduce the amount of space between your molecules, you decrease the bond angles, and so what we find is that these bond angles are less than 109.5. They are less than 109.5. So we want these to be less than 109.5. And again, that is because those lone pairs need more space than the bond pairs, and so they actually push the bond pairs closer together, which gives us that trigonal pyramidal orientation. Now, your book does go on to describe the other kinds of molecular geometries you can have, but please remember, the bond angle is going to depend on what the molecular geometry is. And also remember that electrons don't like each other. And so because they don't like each other, they're going to be pushing away from each other because they have the same kind of charge. And we know that like charges repel, whereas unlike charges attract. Now, in section 19.3, that's where you start talking about electronegativity values. And that is important because we can tell what kind of bond we have by looking at the electronegativity difference. Your electronegativity values, there's a nice table at the bottom of page 385 that gives you electronegativity values for the different elements on the periodic table. So what you want to do is you want to determine the electronegativity difference so you can see what kind of bond it is. Generally, if your bond electronegativity difference is greater than 1.7, then we say that that kind of bond is ionic. If it's less than 1.7, we say it's covalent. If it is between 0.7 0.4 and 1.7, then we say it is polar covalent. If it's between 0 and 0.4, then we say it's nonpolar covalent, or just nonpolar or pure covalent. And what that means is that those electrons are not being transferred as they are in an ionic bond. They're being shared because they're covalent. And again, you see this in nonmetals, but with polar covalent bonds, one of the elements in the bond has a much higher electronegativity than the other. So it kind of pulls the electron closer to it, which is what causes that partial charge or that polar dipole. Okay, and so your book talks about that information in section 19.3, how you determine whether a bond is polar or nonpolar, and you look at those electronegativity differences. And then in section 19.4, it talks about how you determine if a substance is polar or not, the rules that you use. And so what we notice is that if you have symmetry in your molecules, then your dipoles actually cancel out. And so generally symmetric molecules that have polarity in them, they actually end up being nonpolar, and they are nonpolar because the symmetry actually canceled out your dipoles. Now, this section is full of all kinds of information. Some of it is a little bit difficult to understand, but if you do have questions, I have provided lots of resources in this week's materials that you can use. Your review quiz for this chapter starts on page 393, and then the answers for that review quiz are given on page 397. But as always, if you have any questions about the information, please reach out. That's what I'm here for, is to assist you with anything you have questions about. Let me know if there's anything I can do to help you, and I hope you have a good rest of your day.